Hello, hello, hi everyone. Welcome to day 2 of our Unit 3 material. Let's get started. So today is going to be our trig tricks and just how do we deal with integrals that involve trig. A couple of things, just warning, make sure that you can either pause the video now. You have all of your trig formulas handy because they are going to be heavily referenced here. I'm going to have some already referenced in the notes, but as I'm thinking about it, you might just want to pull up on your phone or just on the side like a list of trig tricks. Okay? So let's start off. So first, a couple of rules of exponents. Anything taken to the power of 0 is 1. If we have something to the power of m raised to the power of n, that could be written as m times n power. If we have a times b, all of which is taken to the power of m, we could distribute that power. And if we have a to the power of m times a to the power of n, and that multiplying same a, then we can rewrite that as a to the power of m plus n. Next, we're going to use this main trig property. Sine squared of theta plus cosine squared of theta is equal to 1. Subtracting a sine squared of theta, you can rewrite this as cosine squared of theta is equal to 1 minus sine squared of theta. Keep that in mind because now we have just made a formula to replace cosine squared with an expression that contains only sine squared. Similarly, if you subtract cosine from the sides, you'll have sine squared of theta is equal to 1 minus cosine squared of theta. Now, from here and from here, you'll see in a minute, you have a technical trick. If we divide the whole expression by cosine squared, this leftmost guy will become tangent squared of theta. This will become 1, and this will become 1 over cosine squared, which is just secant squared of theta. Then we have an expression here that involves tangent and secant. You could take this idea and replicate it with over here and over here. Actually, let me cheese it a little bit. I'm going to go ahead and actually divide this by cosine squared of theta and divide this by sine squared of theta. If we do this, we'll have cotangent squared of theta is equal to cosecant squared of theta minus 1. Over here, if I do that, we'll have tangent squared of theta is equal to 1, or not 1, sorry, 1 over cosine, which is secant squared of theta minus 1. Then over here, we see that we have tangent squared of theta, and over here we have secant squared of theta. So hidden within all of these, we have an equation that lets us substitute something for cosine, lets us substitute something for sine, for tangent, and for secant. And then by accident, we have this cotangent, which has a lot of the same properties as this one. But for today, we are just getting into the sine and cosine of it all and the secant and tangent of it all. Okay, some more review. Recall the idea of derivatives of sine and cosine, antiderivatives. Now, remember for sine and cosine, their derivatives occur in this order and repeat in this order, where you have sine, derivative is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is sine, and then it repeats again. If we're doing the integral, let me write that derivative. We're doing the integral, it goes this way, and also repeats indefinitely. And also don't forget ideas of u substitution. Say we're dealing with the hard integral, or not hard, but quote unquote hard integral of tangent. If we're dealing with this integral, then we can rewrite this as sine of theta over, I'm sorry, x, over cosine of x dx. And then remember u substitution ideas, especially the u substitution that refer to when you see a variable whose derivative is also present as a multiplicative product, as a multiplying expression. Sine is multiplying this whole thing. And cosine's derivative is not sine, it's negative sine, but we know that if we wanted to, we could replace it just as well. Doing a du, you get negative sine of x dx. And then because we don't have a negative present, we're just going to go ahead and take it out and attach it to the du of it all. So over here, this becomes 1 over u, and then this is du negative. We know the derivative of this, the integral of this is negative ln of u plus c, and then we want to plug in back u, we'll get negative ln of cosine of x plus c. Now this is to keep us, I don't want to say on our toes necessarily, but it's to keep us sort of just recalling everything we've been doing throughout this class, because it's gonna stack on top of each other. Then we have power reducing identities. We have the sine one here and the cosine one here as well. There's really not much to say. I just wrote them down, but I'm gonna go ahead and leave it out or not touch these any more than I need to. Okay, so for trig integrals, we want to talk about specifically integrals involving sine and cosine. So we have this general format here. Sine to the power of m times cosine to the power of n. We have this sort of flowchart that we can follow. If m is odd, factor out one sign, like this. Convert the remaining sign, because this should be even, into this. Now, we're able to do this 2 idea because we know that any even number we can factor out 2. Then we use u substitution, because now we have made it to where cosines, if we're replacing the u present, cosine's derivative sine appears. Similarly, for when n is odd, we factor out one cosine like so. And because when you factor out one cosine out of an odd n, oh, that's a typo. That's supposed to be n. Let me fix it right now. N. We do get this expression, and we know the derivative of u will be cosine, and we've made a cosine present. If m and n are even, then we have to use power reduction identities and reduce until integration can become direct. If one power is 0, then we can use standard techniques. So keep that in mind. Funny enough, we do have the first scenario be where one power is 0, but to practice we're going to use this ability, because I want to say for this, from the textbook I was using to make these notes, I don't just keep this in mind. Just keep a look on it. I'm not going to say this is a hard set rule, but just keep a look on it, I guess is what I'm saying. All right, let's start here. So we have m being odd. So we're going to factor out one sign. So I'm going to rewrite this as sine squared of x times sine of x. Then I'm going to go ahead and plug in the Pythagorean substitution now we built previously. 1 minus cosine squared of x. Sine of x. Now don't forget the idea we had earlier. Now we have cosine, and we have its derivative appear as a multiplicative product, sine. So that means if I do u to be cosine of x, kind of like what we did up here, then its derivative, negative sine of x dx is definitely able to be plugged in. But the only technicality that we have to do that negative trick, which isn't really that much of a technicality at all. So we can go ahead and here I'm going to do this again. Just I realize I haven't been doing this. We use this to replace cosine, not the square part. And we use this and replace the sine and the dx part. So that's going to be negative parentheses 1 minus u squared du. And then we're going to go ahead and just perform that integral. So if we do that, we'll get a negative. I'm going to do, let's see, I'll do a parentheses for this one. This is going to be just u. And then I'll do minus u to the power of 3 over 3. Close parentheses and do plus c. I'm very near the end. The only thing I have to do left is plug in u back, because the end of this was a problem involving x. So I have cosine of x minus cosine of x to the power of 3 over 3. Oh, and then plus c. And if you wanted to, I mean, I would technically accept that as an answer, but if you're doing the homework and it doesn't match, or there's just some other trick, you still want to be able to manipulate that's negative so it can distribute. Excuse me, I sneezed. Hopefully I muted the mic for that. Okay. Okay. All right, let's move on to another problem. Example 2. So example 2 states that we have an even sine but an odd cosine. So we should probably take out a number from the odd cosine. Let's go ahead and do that. We have integral sine 6x times cosine squared x times cosine of x dx. Replace this with its Pythagorean idea, sine 6x times 1 minus sine squared x, and then times cosine of x dx. From here, we do the other substitution. We want to end up replacing sine. And du will be cosine of x dx. We can replace that to be du. And both of the instances of sine to be just u. And we have the integral of u to the 6, parentheses 1 minus u squared du. Quickly, I'm going to distribute the u to the 6, just so I am dealing with an easier integral. And now I'll go ahead and do the integration. U to the 7 over 7 minus u to the 9 over 9 plus c, and then the last step of the problem, which is to put in back u to be in terms of x. So sine of x to the 7th power over 7 minus sine of 9 of x over 9 plus c. And that's going to be your answer there. Now, next we're going to tackle a special case. What happens when we have sine squared of x? Well, for this, we can use the power reducing formula. For here, we're going to go ahead and use the power reducing formula shown in this very first part right here. And we're just gonna factor this a little bit. Or actually, it's we don't have to factor it, but I'm just gonna choose to out of habit. And from here, you have two options. You can either split these up, and then for this integral, do the u substitution, or just do the u substitution altogether. I think it doesn't hurt anybody to just do the u substitution right now to make this just one variable. So you have u is equal to 2x, and du is equal to 2dx. In this case, you don't have a 2 present, but we know we can manipulate this to just be 1 over 2 du is equal to dx. So we're going to replace this with u. And then we're going to replace this with dx. And you're left with 1 over 4 integral 1 minus cosine of u du. And that just becomes 1 over 4 of u minus, or not minus, because the integral of that is actually going to be, oh no, it is minus, sorry, minus sine of u. And then, am I missing anything? No, just plus c. We plug in back u, because u is 2x, we got 1 over 4, 2x minus sine of 2x. And then plus c. This is technically the right answer, but if you wanted to take it a step further, you could just do x over 2 minus sine of 2x over 4, and then plus c. And you can go ahead and see that this would be the right answer. If I do derivative of that, that'd just be 1/2, which is what that problem is. If I do derivative of this, it would be cosine of 2x, and then chain rule, 2 factors out, and it'd be 2 over 4, which implies the 1/2. Alright, so there you go. Now we're going to follow some similar ideas, but this time with secant and tangent. In this layout, we have a similar tree. And I want to say the typo probably escaped. Oh, no, it didn't escape to here, fine. Okay, if n is odd, factor out 1 tangent times secant. So convert the remaining tangent to be this, using that Pythagorean idea. Use the substitution u is equal to secant, and then notice that secant's derivative appears. Because technically, because u's derivative involves secant, we need tangent to also appear as well. So that's what this taking it out does. All right. Now, if m is even, meaning if m is even and m is greater than or equal to 2, factor out secant squared. So whenever, like for example, if it's m, just written generically, you have secant m minus 2 of x times secant squared of x. Convert that secant into its tangent form. Then you can use the u substitution where u is tangent because now you've made secant square appear. If m is odd and n is even, save one pairing of secant times tangent if possible. Use this Pythagorean idea, and this often leads to integration by parts when only one secant remains. Use u to be secant. If there's only secant and an odd power, you also use integration by parts. So this is just stuff that's kind of inherent. This is more of the trick stuff that we're going to see. So we're going to go ahead and go over that together. Or this is more of the new, quote unquote, new trick stuff. All right. So let's start with secant to the power of 4. So this is the property that stated that m is even and that m is greater than or equal to 2. 4 is definitely even and 4 is definitely greater than or equal to 2. So we're going to do what the strat says and take out secant squared. And then use that identity to rewrite it as 1 minus, wait, 1 minus? I think it's the other way around. Tangent minus. Let me just double check. No. Oh, I was way off. Okay, 1 plus tangent squared of x dx. Because then from here you can use the substitution u being tangent of x, and its derivative appears secant squared of x dx. And it does appear just in full. So that dx and secant just become du altogether. And then you have a super palatable expression. Oh, sorry. I touched the mic. Hopefully that wasn't too annoying. Okay. So then, go ahead and do the integration. We have u plus u to the 3 over 3, and then plus c, and then we plug in back u. We get tangent of x plus tangent to the third of x over 3, and then plus c. And that's going to be our answer. All right. We got to keep it moving. And we now have a situation where secant is an odd number and tangent is also an odd number. So what do? Well, we refer to the very first part of our flowchart that states if n, which in this case is tangent power, is odd, then you factor out one tangent from that. So let's go ahead and first factor out one tangent from that. Oh, sorry. You factor one tangent times secant. So you factor out 2 sets. So you factor out, here I'm just going to write it like this. It'll probably be better. So you get to 3 of x, oh no, 2, sorry, times tangent 4 of x times a secant of x times a tangent of x. Then the strat dictates that you take your tangent and you replace it with secant. So for here, it's going to be a bit tricky because we don't have a formula that says tangent to the 4. But if we use just a quick rewrite of exponential powers, you can technically just rewrite this as tangent squared of x squared times secant of x times tangent of x dx. And this comes from, or it doesn't come from, it technically, not to be annoying, but math has taught you this before, but I just wanted to re-mention it up here on this line. Specifically is this part right here. Just keep that in mind. Sorry, not to be annoying about it. So replace tangent squared with secant squared of x minus 1 squared times the secant of x times tangent of x dx. Now, technically speaking, you can go ahead and divvy this up and, try to get something pretty, but at this point, we can just use the U substitution, and it'll probably be easier using U rather than using, all these secants and tangents. So let's use U to be secant of x. And we know its derivative appears. Secant of x times tangent of x dx. And this is where the highlighting comes into play, because U can replace this guy and this guy. And it technically could replace this guy. But du, which is necessary, needs one secant. So unfortunately, we have to take a secant away from just the u's substitution. And you have u squared, parentheses u squared minus 1 squared. Now this is definitely way easier to do with distributing versus just the repeating secants and tangents. So let's go ahead and just expand this out using just common math ideas. We have u to the fourth plus, no, not plus, because it's negative 1. So minus 2u squared, and then plus 1 du. Distribute that one more time. U to the 6th minus 2u to the 4th plus u squared du. Then do the integration. We have u to the 7th over 7th minus 2 of u to the 5 over 5 plus u to the 3rd over 3 plus c. And then we just plug in back u for all of these guys. We have secant to 7th power of x over 7 minus 2 of secant to the 5th power of x over 5 plus secant to the 3rd power of x over 3 and then plus c. And that's going to be our whole answer. Right? Now we're going to move on to using trig in our substitution. So more explicitly, we're going to deal with these constructed expressions where using the replacement to be in terms involving trig helps us. Now, I don't recall if this strays away from the textbook or not, but I like this version because it's just kind of more like cookie cutter. So we're going to go ahead and do it this way. So we have three cases. Case 1, case 2, case 3. Both of these, or all of these, not both implies to 2. All of these involve a square root, some arbitrary squared variable, which I don't think, maybe in your homework you'll see one, but technically, any number or any, I should say any positive number, right? Let's say 15 is a square, then we know that a must be square root of 15. Yeah, something like that, right? Okay. So the only difference is x is being subtracted or being subtracted by something, or there's no subtraction involved and they're just adding terms. After that, you identify the a. You're going to use this substitution with theta. You're going to construct manually x squared from this. And you're also going to perform the derivative on this side. So you don't have to construct x squared's derivative, you're just constructing x's derivative, which is the whole point. And then you're going to use one of the identities to help us make the problem more palatable. Let me go over the steps in this list. Step 1, identify the case. Step 2, rewrite the entire integral in terms of theta. Replace every x using the substitution, replace the square root using trig identities, and then replace dx with the substitution. So you're going to use these trig identities once they become available in order to help us basically get rid of the square root. Then simplify what's in the integral. Cancel out factors if possible. Rewrite using trig identities. At the end of the day, you want to take integrals only involving sine, cosine, and secant. Then you integrate with respect to theta. Use standard integrals such as sine, cosine, secant squared, secant. Then you draw a reference angle. Why are you drawing a reference angle? Why are we talking about a pre-calc topic? Well, for one, we are stacking math information on top of previously learned material. For two, the whole problem was with respect to x. So we need to draw a reference angle to get back to x. Use the original substitution to build a right triangle. Label the sides using the original x and a. Find all the needed ratios. You are either going to use something like sine inverse is equal to the opposite over hypotenuse, or cosine inverse is adjacent over hypotenuse. Then you're going to go ahead and once you have that theta in that reference triangle, you're going to be able to write theta in terms of sine theta, cosine of theta, tangent theta, and all the trig functions. Do not leave answers in terms of theta. Make sure you convert back to x. Step 7, an arbitrary step, but an important one, make sure you add a constant. The final answer should be all in terms of x with and a plus c. Would that get a lot of points off? No. But it would get like a technical point off. Let's start over here. So we have something minusing an x squared. So this is definitely a case 1 problem. That means we need to use the substitution x is equal to a times sine of theta. But what is a? Well, if a squared is 9, then a must be 3. So 3 sine of theta. Then we need to ask, okay, well, what's x squared? Well, x squared is 9 sine squared of theta. Then we also need to get dx's expression. Dx is going to be, the 3 comes out, and you're left with cosine of theta d theta. Now, with all of these pieces of the puzzle, we should be able to plug in everything we need. I think I want to do everything at the same time. So let's go ahead and treat this like a U substitution problem. Right, plug in this guy. Well, technically it's both of these, right? And then we plug in this guy. But this time, I'm going to just go a little bit different and I'm going to color code. I only want to color code this time around because I want to make sure that we're understanding that this and this are separate parts of the problem, but still literally parts of the problem. So we have the integral of 9 minus 9 sine squared of theta. And then we have the x substitution, which is 3. Oh, wait, that's not orange. Excuse me. Three, fine. 3 cosine of theta d theta. We're going to go ahead and factor out 9 all the way from this problem, which leads us to a 3. In a square root, we have 1 minus sine squared of theta. From here, you know what comes out of sine squared of theta? Well, cosine theta using the identity. And then we're going to go ahead and just do that square, and we get cosine of theta, all of which is multiplied by 3 cosine of theta d theta. Now, let's go ahead and do the whole problem all together. So we have 9 integral cosine squared of theta d theta. We have the issue where cosine is an even number and sine is also technically an even number. So what can we do? Well, we can use one of our power reducing formulas to rewrite this whole thing in terms of a singular cosine. So 9 over 2 integral of, I forget if it's 1 plus cosine or minus cosine. 1 plus cosine. 1 plus cosine of 2 theta d theta. All right. Afterwards, we can just go ahead and do the integral like what we normally would do. Now, the only thing really that we need to make sure we're doing is also u substitution. So let's make sure that we're doing u substitution here. We have u is equal to 2 theta, and du is equal to 2 d theta. We don't have a 2 in the problem, so technically we can write this as 1 over 2 du is equal to d theta. You have 9 over 2 integral of 1 plus cosine of u du. Hold on, I forgot the other one has. This is 1 over 4. Okay. Then from here, we can go ahead and do the integral. You have u plus not cosine, sine of u plus c. And then you're going to plug in back u. Plugging back u, you'll get 2 theta plus sine of 2 theta. Then, from here, we're going to use our double angle formula to make this, or actually, wait. Okay, first we want to deal with everything just being a singular term of theta. So let's go and use our double angle identity to make this be 2 times sine of theta plus, plus times cosine of theta. Okay. Now from here, we have the technical issue that involves the usage of theta. And it's that step earlier where I talked about the reference triangle being needed. Theta from here is actually really easy, right? At this point, we can also distribute the 2. We can do 9 over 2. And it's sine inverse of x over 3. But replacing theta in that context, where it's just sine of sine, is not as easy. We'd still, well, actually, for sine, it will because the inverse cancel out. But for cosine, it isn't as easy. And there's ideally something we can do about this. So just a recap of what I've said verbally, because you're kind of not seeing me right now. Um, I don't mean that figuratively. I mean that literally you are not seeing me. Like I'm only a talking bear. I wonder if I should change my avatar. Never mind, not the point. Um, Sine inverse, right? And sine will cancel each other out. So when you plug that back in, you'll get x over 3. But cosine of theta, you do not have right away. That's where the reference triangle comes out. Using the reference triangle, I want triangle, not triangle. You will have a theta here. And this reads sine of theta is equal to x over 3. So that means x is the opposite, and 3 is the hypotenuse. So we can use Pythagorean identities to get that missing guy, adjacent. Why do we need adjacent? Because at the end here, we need cosine, and cosine is adjacent over hypotenuse. So let's figure that out. We know something squared plus x squared is equal to 3 squared, which is just 9. And we could definitely just work around to get that value. Now we have the answer. We have adjacent, which are written here, over hypotenuse, which is over there. So we can now construct it further to be the square root of 9 minus x squared over 3 plus c. And then technically you can simplify this and the whole thing a little bit more. You can't distribute the 1/2 part, but you could definitely distribute the 9 to be 9 sine inverse of x over 3 plus x times the square root of 9 minus x squared, all plus c. Or you could even distribute the half as well. Either way, um, that is a version of your final answer. Now, a lot of things happened. A lot of things happened that, not that I glossed over, but I kind of acted like they were no big deal. So I want to make sure that I'm sharing with you that it was a big deal. Let's go over what was a big deal. One, using the case. The case is ugly and comes out of nowhere, right? I mean, obviously, behind the scenes, it doesn't come out of nowhere. But I understand if you feel like this comes out of nowhere because it looks like it does, for one. Two, the usage of the double substitution idea. We're using a substitution on top of a substitution. We could get lost in the sauce because remember, if your problem starts with one variable, regardless of how many substitutions you use, you have to get back in terms of that one variable. 3, the idea of getting the reference angle. Why we do that to begin with? Why can't we just figure that out by hand? I mean, not by hand, by calculator, or just some other way. Well, unfortunately, our problem requires us to get as specific as possible. So we want to, if we have the capability, which in this context of cal, you technically do have the capability coming from your pre-cal days of getting the exact measurement of cosine theta, which we made the substitution as x is equal to 3 sine theta. So it's a bit intimidating, I imagine, but it is using and stacking on top of what we know. So we have to make sure that we have maybe not the best foundation, but a good enough foundation. Because at the end of the day, truly, you're not going to learn this without practice and without stumbling a couple times. So that's what the homework is for. The homework is for those stumbles. The test is to determine, well, how well can you do? Because, well, you haven't seen it yet, but I do give partial credit on the test. So you're not like, if you get, like, let's say you get maybe this piece of this problem wrong, you'll still get credit if you perform this and this correctly. But at the end of the day, if you get this piece wrong and this piece wrong and this piece wrong and etc., that's going to stack up and to be more and more partial credit taken off. So please keep that in mind. All right? I don't know why I'm talking like it's the end of the lecture. It is not. We still have about two more problems to go. Let me double check. We have one, two. That's it. All right, let's go. Okay, here we have a sneaky one. The sneaky thing is we don't have a square root explicitly written. We have it hidden. How is it hidden? In this power expression. Now we know that this power, explicitly the 1/2 part of it, can be written as 1 over parentheses square root of x squared plus 4 to the power of 3, and then dx. So we technically know that this square root part is visible now. Now we go to the cases where it says, okay, what substitution do we even do? Well, there is a case where the terms are just adding, and it says to use tangent. So x is equal to something times tangent of theta. But it's supposed to be a. Well, a in this context squared is 4. So a must be 2. So that means we're using 2. And that means that x squared is going to be 4 tangent squared of theta. But that also means that dx is going to be 2 times secant squared of theta. Okay? Don't forget, you're doing the derivative of x. You're not doing the derivative of x squared, of tangent squared. Okay? Let's keep that in mind. All right. Now that we have that in the way, we can attempt to plug most of this in. Okay? Or, well, I keep forgetting it's the whole thing technically. So that can be rewritten as integral 1 square root of 4 tangent squared of x plus 4, all of which is to the power of 3, and then d theta is just going to be 2, which I'll stack right here, secant squared of theta d theta. Okay. I'm just double checking here. Let me go ahead and color code a little bit of that too, because I'm gonna make sure that we're aware of what was replaced. It was this guy over here, and then this guy, and this guy over here. Okay. So now we have that under the way. Let's try our best to get this to be as simple as possible. We know the forest can escape, so it's going to be, I'm just going to write it in full. Well, first, let's do 2. And then we have 1 over the square root of 4, all of which is the power of 3, so it's going to be 8. And then 1 over the square root of tangent squared of theta plus 1, all of which is the power of 3, and then secant squared of theta d theta. Okay. From here, let's do this guy first. That's going to be 8, which 2 over 8 is going to be 1 over 4. And from here, we're going to use that's just secant squared of theta. And that the square power and the square root will cancel out. And then you're left with, on here now I'm going to multiply the secant. You have on the top of the fraction secant squared of theta. And on the bottom of the fraction you have secant to the power of 3 of theta. That will simplify into just 1 over secant of theta. And then that simplifies into just a generic cosine of theta. So pretty simple looking after this. We go ahead and do the integral of cosine theta. That's just going to be sine of theta plus c. And then, remember, our problem started with x, not theta. So we have to figure out what sine of theta is. We were told that tangent of theta, or x is equal to 2 tangent of theta. So that means tangent of theta, which by the way is opposite over adjacent, is going to be x and 2 here respectively. So what's the hypotenuse? Because we need it for sine. The hypotenuse is simply just the square root of x squared plus 4. Because we would just set up 2 squared plus x squared is equal to, we don't know squared, and then we just square root that. So that means sine of theta is equal to 1 over 4, or not sine of theta, this whole thing is equal to 1 over 4, and then sine of theta is the opposite over the hypotenuse, the square root of x squared plus 4. And then, plus c. Yes, am I missing anything? No, I'm not. And again, you could also do the derivative of this and see if you do get this value. So just keep that in mind, just in case. All right, we're going to do the last case of the day with example 3. It will be case 3, I think. It's the x being minus by something, so I think that was the last case. And it was. So that one says to use something times secant of theta. And that also has an a in front of it, which a squared is 16, so a must be 4. So that means x squared is 16 secant squared. And the derivative of secant squared dx is equal to 4 tangent theta secant theta d theta. Okay? Then from here, we can go ahead and just plug everything in. I'm going to go ahead and do the highlighting for this. For this. And this time, I think I'm going to leave it on the actual top, because here we didn't benefit from writing secant on the side. So I'm going to take a risk and see if writing on the top is going to help me a bit. We have 4 tangent of theta secant of theta. I will obviously just do the d theta on the side. Is over the square root of 16 secant squared of theta minus 16. Factor out the 16 will, and under the square root will be 4, and 4 divided by 4 is 1, so that's going to cancel out. So you're left with tangent of theta secant of theta over the square root of secant squared of theta minus 1. That has a trig trick that will get replaced by secant squared. And we know secant squared, square rooted, is just secant. And then that whole thing will be able to be canceled out. Hold on, I want to make sure. Oh. I don't know why I rewrote as secant. It's tangent, my mistake. I was wondering because I was like, no, the answer doesn't make sense. Now it does. Okay. So this whole thing will cancel out. If the integral of secant squared, or secant of theta. In that case, the integral of secant theta is just our, do we do this by, do we practice, hold on, I'm thinking, well, how long has the lecture been? Oh, the lecture's been close to an hour. Do we practice the integration tricks? I want to say this is one of our common integrals, but I don't remember and I don't have all of our resources attached to me. Do I make it a learning lesson? I think I could make it a learning lesson. Okay, let's try it. So, from our previous steps over here where m is odd and n is even, because technically it's an even number, we can take out one of these guys. So let's go ahead and take out secant of theta, tangent of theta. Remember, there's no tangent to take out of, so we technically have to write it as 1 over tangent of theta. Then, oh, d theta, excuse me. We see that tangent's derivative, secant and tangent appears here. Wait, did I say that right? Tangent's derivative? No, tangent's derivative is secant squared. Um, one over cosine, we could do that. Hold on, give me a moment. Let me cook. Let's see. If I don't cook in 10 seconds, then I don't think I want to cook at all. Or we can use integration by parts. Let's try using integration by parts just real quick. If it doesn't work, then we'll just use the formula. Let's see. Let's set u to be secant of theta and du to be secant theta tangent theta d theta and dv to be d theta and v to be theta. Um, no, because then this derivative is unnecessarily complicated. Um, hmm. Might I might look this up and then show you on the group work video, but I know the formula is the integral is going to be ln of tangent of theta plus secant of theta. Let me double check that. Yes. And then plus c. And then we would just do the reference triangle to get tangent of theta and secant of theta. Secant of theta is equal to x over 4, which is hypotenuse over adjacent. So we know we build this, it should be x squared minus 16. And then we should be able to plug in both tangent and secant respectively for these guys. We know that ln of tangent is something new, it's just opposite over adjacent. Square root of x squared minus 16 over 4, and then plus secant, which technically is in the prompt. It's x over 4. And that would be your answer. Okay. I'm going to double check and see if the integral of secant is something that's given. If not, then I'll probably, in the first page of our group work, go over that integral. Okay, that's going to wrap up today's video, guys. Let me know if you have any questions. I'll see you in the worksheet video. Bye-bye.